Quantum Foam, Episode 20, Quantum Mechanics.
Quantum foam.
Physics. Physics is at the foundation of all the mathematical principles that guide the heavens. You have to understand physics.
More than likely that's not going to happen, but
Forces which govern the universe. Physics.
okay, so we've been doing a lot of very fucking complicated shit with this. I figured I would throw some other shit in here because I want this to be a fun show where different things go on, we make fun of people, we talk about a bunch of shit, and make a thing about it.
Can't stand it. You sound like a bumbling fool.
We've been going into some serious materials. Each 10 episodes, we get deeper and deeper into this. From 1 to 10, we did a whole thing. And then from 11 to 20, we're doing a thing. Some of these topics from 11 to 20 have been some serious fucking topics. We're finishing it off with episode 20 and going over quantum mechanics. I mean, this is a little bit upper undergraduate type work. We're talking about just quantum mechanics, not the other crazy theories and other shit that I've been trying to go over. That's the whole point of the show and stuff. But, I mean, how are we actually going to go through this stuff? How are we actually going to see this stuff? 1 second here. It's the stuff of figuring out quantum physics. Dealing with things of the very, very small. Not things the size of us and planets and cars and bigger stuff. Fucking quantum mechanics. Wow. There's a lot of stuff out there on this stuff, but it gets so complicated and so detailed. What do we even go over? We're going to be going into
quantum mechanics, my specialty. I like to say that about the popular theory of the day.
the issues of putting two theories together have always been with the quantum, trying to get quantum field theories, quantum mechanics, and other quantum theories of physics and other quantum theories of gravity to actually mix with relativistic gravity, Einstein's gravity, curved space-time, stuff like that.
To grasp the nature of these things takes more than just an advanced graduate degree, such as a PhD in physics. Postdoctoral work is likely required.
Good thing we have 500 hours to do this. We're only approaching the end of 10 hours of stuff. I am only 1/50th of the way done. This is going to be sort of the goods. We have time to get into the very fucking complicated shit that is the theory of everything. Each episode is your quantum foam of that. It really is your quantum foam, man. I'm not lying. I swear it. I swear it.
Physics.
Quantum mechanics. It is a math mechanics. The thing is I'm trying to waste time on this one because we only got a half hour and I don't want to go over all this bullshit in quantum mechanics. I have so many details here that I couldn't fit it on a third of a page. I wrote another half page of notes. All right, let's do the dirty.
Forces which govern the universe.
You're taking a physics undergraduate, you're going for a bachelor's of science or possibly a bachelor's of arts if you're going to teach this shit, if you're hardcore into that. They say if you're not actually doing research, you can become a teacher. Man, fuck that. Some of these guys were some of the best teachers. If you're a teacher and you're a director of a department at a prestigious college and you are literally teaching students and assistants and they are becoming Nobel laureates, that's good. That means you are more important than even all of them, per se, because you're steering them in the right direction. You're taking a 4-year undergraduate course in physics. You take your physics 1, 2, 3, all calc-based. You got your Newtonian mechanics, you got your thermodynamics, and you've got your electric type physics that covers in 1, 2, 3 physics. Then after that, you go into mechanics. That's basically differential equations. You got to do calc 1, 2, 3, diff EQ before you can even do this because mechanics is calculus, essentially. Then further, a junior-senior course, probably junior, quantum mechanics itself. Only a 3-credit class, but you essentially already know mechanics, so now you apply it to quantum mechanics itself. So that is what we are doing here. What is this? Quantum mechanics is restricted to discrete values. This is the process of quantization. I kind of want to go over some of these bigwigs because you need to know them because they are built right into quantum mechanics. Max Planck, 1900 and 1905, turn of the century. The older grandfather, so to speak, he was of age before everybody else. Einstein's 26 in 1905. Max Planck's older by that point.
He was born in 1858, compared to Albert Einstein, born in 1879.
It's like, I'm going to be taking a look at this very closely. I mentioned this in previous episodes, looking at the Planck stuff. Max Planck, he dealt with black body radiation, quantum mechanics, the photoelectric effect. That was one of Einstein's papers. He had 3 or 4 or 5 seminal papers, and one of them was on the photoelectric effect. Remember, that's the reason why he actually got the Nobel Prize later on. It wasn't even for, it's like they wouldn't give it to him for E equals mc squared. It's just so simple. The implications of that, the predictions of that have been proven experimentally for 100 years with absolutely no variations. What Max Planck did was he calculated his Planck constant.
The significance of that is that constant is very, very small, but not zero. It has some size, not no size.
And the Planck constant is essentially your Planck constant over 2 pi. What this really does is it makes discrete energy levels out of your waves so that, in effect, they can be treated as particles. It's used in almost every aspect of quantum mechanics. Tell them that value real quick, Newton.
Planck's constant, denoted by the lowercase English letter h, is equal to 6.626 times 10 to the negative 34th power joule seconds. But remember, physicists often reduce it over 2 pi, which then equals about 1.05 times 10 to the negative 34th power joules times seconds.
Alright, who else we got here? Erwin Schrödinger. Erwin Schrödinger. Everybody's heard of him. Schrödinger's cat. You have a box. It has a lever in it that will expel a radioactive material. There's a cat inside. The cat is both alive and dead at the same time because people are finding out that when you are making a measurement, you are choosing the state of the cat. So he's alive and dead until you check to see if he's alive or dead. It's a little more complicated than that. The uncertainty principle is the foundation of quantum mechanics. Werner Heisenberg. Most of these things were figured out in the teens and then in the 20s. The 1920s were very, very important. 22, 25, 26, 28. Werner Heisenberg, 1925, was his extremely important paper on the non-commutability of quantum states. You've heard of logic, right? PQ logic, QP. If PQ, then QP. The thing he was figuring out was if PQ, then not commute to QP. And so that is a very, very strange phenomenon. And we'll get into more of that later. Obviously, you know the Heisenberg Uncertainty Principle. You can't measure the momentum and the position of a particle at once. The speed, the direction, the momentum. That's the speed, direction, force, momentum of a particle, and the position. Keep this in mind. When you actually measure a position, you can put it in a 3D grid. But when you measure the speed, what is a speed? A velocity is actually a position per time and a direction. So how can you calculate a position and then also separately a position per time? It's in both spots. You can't do it. As you measure one, the other one gets more inaccurate. More on that later. Another guy, Wolfgang Pauli. Pauli Exclusion Principle. The Pauli Exclusion Principle. Again, 1925. They're figuring this out for electrons because obviously that was the first subatomic particle figured out and discovered.
J.J. Thomson, 1897. He was studying cathode ray tubes.
They shoot gold through a plate. We're sitting in a dark room and it's like, we're getting dots here. And that doesn't make sense. What is this? It's an electron. Electrons are hitting it. It doesn't make sense.
There is a lot of things here.
What is this?
Also Dalton's atomic theory.
And that doesn't make sense.
Better wait to go into much of this stuff though until they are better prepared.
And that doesn't make sense. The exclusion principle was then extended to fermions later on, about 1940. This is when they had it fully developed, running up to World War II, right around the time they were starting to develop the nuclear bomb. Spin Statistics Theorem, 1940.
In other words, the Pauli Exclusion Principle.
All half-spin particles. 2 identical fermions cannot occupy the same state. They can't occupy the same quantum state. There can't be 2 electrons in the same position around an atom.
Anywhere, really. But around atoms is where electrons like to hang out.
We need to go into particles. Here's the thing. We're going to be describing some of these particles here and the differences therein before we even go over the standard model of particle physics. Particle physics is just a fucking zoo. It really is. There's so many. It's just how you refer to the stuff. I don't like the fact that a lot of this stuff is named the way it is, and I'm really going to be digging deep into this stuff. I have not done a large amount of quantum mathematics because we already have these equations in the math form. for it, the matrices for them. So I'm going to pick them out and put them into mine later. I just need to make sure that you guys understand what what shit is. The novice, the non-physicist, the prospective physicist or physics student. You need to know some of this stuff. I'm not going to just be like, oh, quantum mechanics, you like a couple things about it. Fuck that. We're going deep in this bitch. All right. Fuck that. We're going deep in this bitch. So, fuck that. We're going deep in this bitch. So, fermions, electrons. Fuck that. We're going deep in this bitch.
Okay, mister. Put the beer bottle down.
Half-spin particles, lots more. Bosons have exact integer spins. They're not subject to this exclusion principle. That's Wolfgang Pauli. Important people. Pauli. Important people. Pauli. Who else? Bigwigs. Max Born. This was the very first attempt at formulating some kind of mechanics for quantum mechanics, and they call this matrix mechanics. Max Born.
Ja, es gibt auch Paschal Jordan.
Quit fucking around. Paschal Jordan. He, Born, and Heisenberg made the first attempt at a so-called matrix mechanics formulation of quantum mechanics.
They like to use the name matrix, but really all it is a 2x2 grid. We're getting into matrix theory with our stuff, and I'm trying to develop a larger, higher matricey mathematics theory. Matrix theory, linear calculus, I don't know if it's a theory or not. It is a methodology that I'm explaining. So we've already went into that a little bit. We're going to get deeper into it. Max Born and Werner Heisenberg in 1925 formulated this matrix mechanics. Then in 1926, around the time of these conventions and when they're trying to figure this stuff out, and the smartest people in the world essentially are getting together to figure this stuff out. They're writing each other back and forth. This is how they did it back then, through letters. I'm doing it through this because we got technology and shit. They did it through letters back then. We could do it that way as well, but I'm doing it with sound because I can. So in 1926, this psi function. What is this psi function? It looks like a little dash with a U in it. Capital Psi, Greek letter.
More like a vertical dash, or an I with a U on top of it, like a little three-pronged fork. The prongs go upward.
It is for your wave function. Now, we are going to be revisiting this wave function multiple times. In 1926, they developed this wave function, this psi wave function. It determines the probability density. It is the probability density function. One of the main things that Erwin Schrödinger did was come up with his equation. I'm not even going to be writing this stuff down yet. We've sort of spoken of it. There has been reformulations of this equation multiple times. I may reformulate it myself. However, I am rather young, so some of this stuff takes like 10 years or more. I'm going to get balls deep into this shit. Trust me, I am. Balls deep. I am. All right, so what was done? What did Max Born do? What did they do in this 1926 psi function, this wave function, this Schrödinger equation that they are formulating? The Schrödinger equation essentially is it. You can reformulate it however you want for your own purpose, but it essentially gives you the probability density function in the Schrödinger equation.
The goods, as you like to say.
The best thing he's known for, Born, is his statistical interpretation of this wave function. That's most of what this is, statistics. Bose-Einstein statistics, bosons. There's Dirac other statistics, and we'll get into that too. You've heard me say the Dirac equation. That's a reformulation of the Schrödinger equation. It's been done multiple times. I said like 4 maybe? I don't even know. There's probably 4 on this paper right here, but it's probably been done dozens of times. But the highest caliber of academic abilities have brought us these statistical interpretations of this wave function which describes your quantum states in quantum mechanics. You use quantum mechanics to do this stuff. One thing I was going to mention, Born went to the University of Göttingen, and Göttingen, Germany, Lower Saxony or somewhere. Pretty important college of the time. In 1904, he began going there, and who he found there was Klein, of the Kaluza-Klein 5-dimensional model. David Hilbert. Hilbert spaces are very important. I believe in Hilbert spaces. That's the type of spaces that we're going to be using. Also, Hermann Minkowski. Minkowski space-time, where
the framework describing the curvature or expansion.
It equals 0. It's not anti-de Sitter, which is negative, or other positive types of spaces. Minkowski is neutral space.
Max Born.
He joined this college where there happened to be some of the smartest mathematicians that the world has ever known. There's a lot of math in here. These aren't all mathematicians and physicists. Not all physicists are excellent at math. I am developing a higher math than all this lower stuff. Most of this is statistics. They write this shit after the bigger math.
If ever in doubt, write a new mathematics. That's what I did. quantum gravity isn't going to write itself.
Not precisely. Technically, if he writes artificial intelligence, which then writes the quantum mechanics, would it not actually be writing itself? I think so.
All right, we are about halfway through episode 20, Quantum Mechanics of Quantum Foam. Quantum foam. When you make your associations between ideas, such as Einstein, some of his notation for some of his stuff implies mathematical operators. That's when you're making an association. And he definitely made some. Fucking 16 years old, wondering what it's like to ride by a light wave. I don't think I was even that deep into it at that age. That is quite awesome of him to do. So, some other guys. What else we got here? Who else is important in the development of quantum theory and quantum mechanics? We have Paul Dirac. The Dirac equation, his formulation of the Schrödinger equation in 1928. This describes, again, all half-spin massive particles, such as the electrons and quarks, etc. This was validated by accounting for the hydrogen spectrum that we see everywhere because there's so much fucking hydrogen. It's the most common element in the universe.
The famous 21 centimeter line.
It has its merits and its uses for various things. His equation was definitely validated by accounting for the hydrogen spectrum that they were able to see experimentally. Paul Dirac, he was a Lucasian chair.
Lucasian chairholders fuck the world.
She wants some of my Lucasian chairholder pimp juice.
There was only like 16 or 18 of those guys, and obviously Stephen Hawking was one of the last before he retired, right?
Damned right, playa.
And then back at this time, Dirac, he was an English guy, Cambridge, math chair guy. Essentially the smartest mathematician in the world, and actually doing stuff with it. And not just smart and not doing something with it, like I've known people to be. I knew a guy who had an IQ of nearly 200. He became criminal, hacking into this, hacking into that, jacking money. He was smarter than Einstein and he could have applied this. I think that the reason why I'm able to do this is because I'm just average enough and just smart enough to just be average across the board. I've been tested, my IQ is 142. That's pretty fucking high, but it's really not as far as these motherfuckers. Most of these motherfuckers' IQs are probably there or above. They studied and they really made some serious contributions to science as a whole, and especially quantum mechanics. This Dirac equation, it actually implied the existence of antimatter even before anybody knew what it was. This is how phenomenology works. This is where you can have theoretical physicists sit at a pen and paper and then say, hey, administration, this is according to Feynman, administration of the telescope, you should look and see if you can see Neptune there. And they're like, what? That's bullshit. And then they did another one. That's bullshit. Okay, that's bullshit, but we'll still do it anyway. That's bullshit. That's bullshit. That's bullshit. That's bullshit. What do you know? They discovered it. Because there were physicists sitting around calculating fucking gravity. Remember, they couldn't see the edge of the solar system with these telescopes. The phenomenology is the bridge between the math and the experiments. These guys did a bunch of math. They came up with predictions. This is where they confirm them experimentally. So the Dirac equation definitely did that with antimatter, of course. It's worthy to mention what they really are doing at the collider is Monte Carlo experiments. We'll get into that a little bit later, but essentially they use repeated random sampling to discover distinctive traits of things when they're doing experiments, when they're actually doing experiments. And that deals with operators and a bunch of other shit. I'll mention that later, but for now, let's get into more of what this quantum mechanics is and how it deals with your wave functions and your operators. The two main variables are your position and your momentum, obviously. They're trying to describe quantum particles, quantum states of subatomic and atomic particles. So this goes into atomic physics and particle physics and quantum physics and other stuff above that. Position and momentum. Quantum mechanics treats time differently than general relativity, and that is a major fucking problem. You gotta deal with your space-time as though they're
like there is only 4D math.
Only 4 dimensions. Time is just the same thing as width. But width can go forward and backward in space, but time can only go forward in time. Maybe it can go backwards. Maybe it can't. Stephen Hawking, didn't you?
Yes, I did.
Yeah, you explained this. I read in one of your books.
Let's not get too deep into that. We don't have the time to discuss it fully here.
There's pretty good reasons why time probably can't really go backwards. So what is this quantum mechanics doing? It's treating time differently than general relativity. It is using things called path integrals. essentially path integral approaches to quantum mechanics. All of this stuff, you can describe it as a quantum state vector. You can just call them a vector when it just describes the math for something. It's a vector. I'm giving you a fucking vector. Fucking theory of everything vector, bitch. It looks like this. 500 hours of bullshit. That's what it is. Fucking. No, there's some bullshit in there, but that's to keep everybody sane. The problem with uncertainty states you can't have the known value of this and that one to 100-degree accuracy. So deterministic and causality may be out the window. We are trying to figure out here very earnestly, we are really trying to figure out what are these processes, these physical phenomena and these processes of nature. Are they deterministic or stochastic? We don't know, probably stochastic, but partly fucking deterministic. Newtonian physics is pretty fucking deterministic and causal. So pretty important stuff. There's the Planck constant, h over 2 pi. There is the psi equation. It is your state vector in your quantum system. So we're really describing positions of electrons and such, and other particles. Wave functions of the electron in a hydrogen atom, they go at different energy levels. Quantum mechanics can't actually predict the exact location of these particles, just the probability of finding it. So they've mapped out some stuff of the hydrogen wave function, and generally you can see the states. But there are chances that they won't work out the way we think they will, and supposedly quantum mechanics can be applied to macroscopic phenomena like us. So there is some very, very, very small probability that right now a feline cat will just randomly appear on my desk and then disappear again. You could do the math for that, but we don't need to do that here. But
quantum tunneling, d1 over that sometime 2.
That demonstrates that quantum mechanics is supposed to be from the small on up to the big. Obviously, general relativity is not up big on down to the small. There's a disconnect, a very fucking serious disconnect. But the idea of quantization, it was verified by atomic spectroscopy, looking at these atoms, looking at the hydrogen atom, and really, really looking at your hydrogen wave function. This idea of wave-particle duality was agreed upon by Einstein and everybody. Born, Heisenberg, Bohr, Schrödinger, Pauli, Planck, everybody agreed that there is a such thing as wave-particle duality, and it's still technically unsolved, but there were very important experiments that determined this. And what were they? Well, one of these was the Stern-Gerlach experiment. This actually happened in 1922, and what they did was they set up a little experiment. There's an electric field, heater, whatever. They shoot a couple silver atoms, and they expect it to be this, and they actually see this. What they see is these half-spin particles. They found out that they're half-spin particles and not integer particles. So your fermions and your electron stuff is different than your mass particles. Your photon is massless, but your electron has mass. There are certain things like mass at rest and mass in motion. If a particle has any mass at all, then it can't go the speed of light. It could only go 0.999999 the speed of light, 99.9 the speed of light. And they have done this experimentally at CERN and Fermilab. Those are particle accelerators, obviously. This is what they do. They come up with a theory, they use quantum mechanics, and then they test it with their colliders. They smash particles, they see directions and such. But back to the Stern-Gerlach experiment. 1922. This happened right before all these guys are figuring this stuff out. They found out that a particle should be here and here if they're integer spin, but since they are actually half spin, the other positions where they hit on your photodetector plate is different. 2 different directions. They have to be half spin.
The position the particles hit are different places than where they expect. That is how they know that certain particles have a less than full integer spin.
Figuring this out, shooting through a magnetic field, they're observing the deflection. The deflection actually shows these particles are half spin. What are some of these other particles? These hadrons. The LHC, Large Hadron Collider, is dealing with hadrons, which they say large because they're bigger than some of the other stuff, and that's talking about their mass. A hadron is a composite subatomic particle. They have 2+ quarks, and they are held together by the strong nuclear force. And remember, the weak nuclear force instantiates or induces radioactive decay. Madame Curie had to figure that out the hard way. Very, very dangerous stuff. But hadrons are held together by the strong force. So they're smashing them apart in these particle accelerators, and they are breaking apart. The amount of energy that they are expelling is enough to break apart the strong nuclear force. And so that takes a lot of energy. They got the Hadron Collider up to 16 tera-electron volts, which is pretty fucking high.
That really is a shit ton of energy. That is the energy of about 16 little mosquitoes flying around, but then shrunk down 1 quadrillion times, a million times. So put like that, yeah. That is a shit ton of energy, bro.
We'll go a little bit more into some of this stuff here. Enrico Fermi. This is starting to get into the nuclear reactor. He created the CP1, the first nuclear reactor in 1942. So, the Fermi-Dirac statistics. This is Fermi stuff mixed with Dirac stuff. They derive some of the same stuff at the same time, but Dirac gives Fermi credit, but, Dirac knew what he was doing too, and they did it both individually and right around the same time, but Fermi was a little first. But this Fermi-Dirac statistics, distributed particles over energy states. They obey the exclusion principle for half-spin particles. You get into this stuff, Fermilab, Fermi paradox. There's a lot of stuff named after this guy.
I think the aliens just don't think that we are any smarter than we think of little ants and bugs.
Yeah, that's a good one. I'm Joe Press. Get in the car.
Whatever.
Let's get back to the subject. There are those, such as Lee Smolin, who believe that even freshmen in college should start taking quantum mechanics. We have a lot to cover.
Okay. This Fermi energy is the energy difference in a quantum state between the highest and lowest occupied single particle state, like a Fermi gas. Paul Dirac here, 28, did his equation, all that, and gets into the deep shit like self-adjoint operators. Creating a linear map that is its own adjoint. They call that a Hermitian operator.
Phi and psi variables. It is a matter of convention.
We'll get into that later as well. What else is there? There is your different wave functions, Schrödinger equation, time-dependent or time-independent, depending on what you're doing. It's statistics, probabilities of finding a particle in a certain location. There's also the Lippmann-Schwinger equation.
And that just deals with
Particles.
scattering.
There's so much stuff we can get into with this. I could go on and on forever about it, but I want to make sure that we go over some of the basics of quantum mechanics so we can actually maybe do some quantum mechanics possibly in the next 10 episodes. I want to finish these 10 episodes with a bang. We started out with chromaticity. We went deep into lots of different things. Theory, string theory, all of that. The last 3 were pretty much doozies. I'm trying to solve this, and I haven't even started doing the math yet. Well, I have, but I know how to do math. I've studied. I've learned this stuff. I'm studying more. I'm ever studying more. I haven't even started doing the math yet. What we're getting into here is your Schrödinger equation and how it's a given solution for a particle in its wave function and your psi function. So the probability can be written as your square root of your psi function. And this is for your confined particles.
Locality, non-locality, that idea.
Obviously, a lot of this stuff was built on Maxwell's equations, has dealt with your light, large amplitude is this and that. Max Born put it together in quanta, Schrödinger, Heisenberg.
Are you certain? Sorry, had to at least once.
Heisenberg let you know the uncertainty of it, which is funny because he's sending the stuff to Pauli, writing them, and he's still uncertain about whether or not, obviously, man, he's uncertain about the uncertainty principle. What do you know? Wolfgang Pauli Exclusion Principle, very important. Max Born, matrix mechanics, probability density, statistical interpretations of the psi function. These great mathematicians that he went to school with.
Nuclear physics had quite the heyday.
It gets into nuclear physics with Enrico Fermi later on, 38, closer to World War II. So for now, this is all we're really going to go over dealing with quantum mechanics. It's essentially some serious mathematics that deal with position and momentum to describe quantum states. We're not even getting into quantum gravity or other phenomena in the quantum. We're just talking about quantum mechanics itself here as it was written by these guys. And the photoelectric effect, you shoot a light at a piece of metal. According to various things that were understood in classical Maxwell's equations, higher energies, there's a UV problem. Higher energies, it shouldn't shoot out particles until there's higher energies. So they had to figure out a way to get around this. And the way they did that was Max Planck. And he did that and set the stage for these guys. Then they found out the problem with quantum phenomena is that you have to deal with statistics. And that's it. We don't even have time to go into quantum electrodynamics or chromodynamics.
In the next 10 episodes, we will cover more specifics.
Those are essentially further revisions of quantum mechanics that try to reconcile general relativity and quantum mechanics. They can only do it so well because we're talking about statistics here. Are your Hermitian operators good enough? Are you dealing with self-adjoint operators? Some of this stuff I'll probably even cut out. You don't even need to know it. But for now, we are going to finish this strong. That is a run-through course on quantum mechanics. For now, that is it for episode 20 of Quantum Foam.
Quantum foam.
The zeroth wave disclaimer.
The views and opinions expressed in this podcast are those of the author or authors and do not necessarily reflect the particular views, thoughts, or opinions of Zeroth Wave Productions, any of its sister companies, its parent company, Zeroth Enterprises, or any other entity which had existed, will exist, or which, quote-unquote, presently must exist outside the realm of our current space-time.
Quantum Foam is produced by Zeroth Wave Productions.